Hello everyone again. So let me continue with the same chapter on Planck distribution, but we're going to move to instead of doing a black body radiation, we are going to look at vibrations in a solid. So the first model for this is essentially Einstein model. So the idea is to be able to describe the heat capacity much more closely, heat capacity of certain solids much more closely with respect to the experimental results. So let me just mention this. So atoms in solid vibrate about their equilibrium positions. And one of the things that we think of, let's suppose you consider n atoms in there. So that gives you, say, 3n degrees of freedom. And each atom has an average energy of kBT. And the expectation over here is that your molar heat capacity for 1 mole will behave in the simplistic sense, will behave in the following way. 3 and 8 is the Avogadro's number times Kb equals to 3R. So this is known as the long Petit's law. Of course, this is a gross simplification to expect your heat capacity to be just simply constant. So here is where we try to introduce heat capacity with temperature dependence. So Einstein sort of pointed out in 1907, says that just like in the case of the black body radiation, we have quantized energy. So here again, it posits quantization of energy for the oscillators or the vibration. Vibration and solids. So in other words, what we have done for the case of black body radiation can be followed through with some modification on certain parts. So let me just write that down. So one of the things that we can actually write down, for example, is the free energy. So we have F equals to, let's say the oscillators will execute a certain amount of energy with respect to the vibration, and then you have this part, which is the one that gives you the temperature dependence through the Planck's distribution law that we had earlier. One minus E, sorry about my handwriting, maybe I'll make this properly. 1 minus E minus H bar omega alpha on KBT, where the sum alpha here is essentially coming from all the vibrational modes over all vibrational modes. So Einstein's model sort of give a kind of simplification for this. So Einstein model assumes that all these frequencies are the same. Which is given by this symbol omega E, which is called Einstein frequency. Okay, so plug that into the free energy, then we essentially have F equals to N epsilon plus K, plus, I will explain this later, 3N KBT log of 1 minus E minus H bar omega E on KBT. Now the sum is over all possible vibrational modes, so there are n atoms and there are 3n degrees of freedom, so that gives you the 3n there. Okay, so one of the things that we want to see, as we said earlier, is to connect with some physical observation. Particularly we want to look at the molar heat capacity, how it deviates from the DeLong-Petit's law. So here we already have seen in this particular case that free energy is related to some other thermodynamical variables, for example entropy, and from entropy you can actually get your heat capacity. Which is given as minus the second order derivative of the free energy with respect to the temperature. So let's try to calculate this just to give you a feeling of the calculations involved. So this is second order derivative. Let's do the first order derivative first, minus ddt of the free energy. So over here, the temperature dependence over here is coming from this factor and also this logarithmic factor. So we do step by step. So the first one is easy. It's just a linear in t, 3n kb, and then you leave the log known. And then the next term is to differentiate the log. So plus 3n kb t. Differentiating the log will give you 1 over the argument of the log. And within the log, there's an exponential function. Okay, so you have to remember the exponential function is multiplied by negative sign, and then the exponent also has a negative sign, so that gives you the following: E minus h omega E on kBt. And inside this exponential, the exponent itself is a function of t, so you have to differentiate that. And again, there's a minus sign here, and then we differentiate t at the denominator, there will be another minus sign. So that gives you h bar omega E on kBt squared. So let's simplify the second term so that we can do the next order of differentiation easily. That would give you plus 3nkb. Your t will cancel with this t squared there, and then you have the 1 over 1 minus e minus h bar omega E on kBt. And then you have the exponent here. I'm going to do the following. I'm going to take this exponent, divide it top and bottom from the factor here. So let me just get rid of this, simplify it further. So this will be 1 over E h bar omega E on kBt minus 1. Okay, you divide top and bottom by the same, this particular exponent, so you get that. And then essentially the other factor is this, with only, it's doing that, kBt, not the square. Now we can differentiate this. So I'm going to just write down, it's pretty long, just to show something which I still have to figure out what's going on. Make a mistake somewhere. So the first derivative is for the first term, the temperature dependence is in the log. So again, you do the same just like before, 3 and kb, and then you have the 1 over 1 minus E minus h bar omega E on kBt, and you have your E minus h bar omega E on kBt, and then the factor of h bar omega E on kBt squared, just like before. Okay, and then we need to differentiate the second term. So there are two factors here that depends on t. One is this factor and the other is this factor. So you differentiate term by term. So let me just write down the answer. Minus 1, and then you get a square there from the differentiating that. Then you remember you still have to differentiate the functions inside there. So that gives you, let's see, first the exponent, and then the exponent in the exponential gives you minus h bar omega e on kbt squared, and then you still have this factor which we have not differentiated. You have h bar omega e on kbt. And finally, we differentiate the last factor, which is that gives you plus 3n kb 1 over e h bar omega e on kbt minus 1 minus h bar omega e on kbt squared. Now, if you simplify the first term, you will simply cancel off with this. Remember that this has a minus sign here, and you're left with only the second term, which could be simplified. There's some problem with this, but I hope you can check this later on. 3n kb, and then you have this thing squared. Your t squared over here is going to cancel off with 1 over the t here. So that h bar omega e on kbt square I've forgotten about the eh bar. Yeah, it's there. Eh bar omega e on kbt divided by eh bar omega e on kbt minus 1 square, and that's it. Okay. My problem was to figure out what happens. Somewhere along the line, I must have made the wrong sign here, because here you have a minus sign here, minus sign here. So 3 minus sign, that's supposed to give you a minus sign instead of a plus sign. But no, I'll let you check for this. But important thing is that we have now the time dependence for your heat capacity. So let's check at certain limits how this turns out to be for high temperatures, excuse me, where you have kBT bigger than h bar omega e, say, then you will find that your CV goes to 3n kb. Okay, so in other words, all this term sort of disappears, because this is going to be large. Okay. And for lower temperatures, your CV is going to be related to this exponential here. So here you have exponential on top, and then here you have exponential with the square term. So essentially this will be looking as if it's decreasing as a negative exponential. In particular, when t goes to 0, you also have your capacity, heat capacity to be goes to 0. And this is consistent with the third law of thermodynamics. Consistent with. Okay, so that's encouraging. You have a high temperature limit that gives you a constant, and at other temperatures there will be this dependence on temperature. So let's look at the picture of a graph here, which is plotted for the case of a diamond. Diamond shows, no, diamond doesn't actually behave according to Dulong-Petit's law. So this is actually for the diamond. So oops, should capture that rather than take a snapshot. Again, so paste it here. So you can see over here, for example, as temperature goes high, this is sort of levels off, and then as it goes down at the lower temperatures, it goes like an exponential at some parts, but really there are problems over here. So there's some leveling off there, which doesn't quite correspond to the exponential decay. So so the Einstein model works well. To give the temperature dependence, but at lower temperatures, some deviation. So we need to address that. Okay. So there is another model that we need to go through. Let me clear up this thing. Now, we have seen earlier that one of the assumptions, which is not really realistic, that Einstein assumed that, well, Einstein is aware of what's going on, but the simplification that Einstein made was to assume that the frequency of the vibrations are constant for all oscillators. So this is not quite realistic. So Debye sort of consider a model which is going to be, your frequencies can lie in a certain range. So let me just do this. So what Debye's model did was to use density of states for which you can actually look at the modes of vibration within certain interval, omega plus d omega. Okay. And what one does is to write down the density of states. Previously we had density of states written in terms of the wave number. Here we are writing in terms of the frequencies, angular frequencies really. So remember in 3D we have this volume factor divided by 2 pi square, and then you have your previously it was k squared. Here we're going to get your omega squared. Okay. Here's Debye introduce a few things. So let me just write that down first. This is SL cubed plus 2 SL, sorry, SE cubed, then multiply with this d omega. So what is this SL and ST? Essentially, what Debye assumes is there are 3 modes of vibration. So the longitudinal modes, which is like your sound waves, will travel with certain speed, travel with speed speed as L, and for the transverse modes, travel with speed as T. And there are two transverse modes. Okay? In 3D, you have one mode is the elongated mode, and then the other one is the two different transverse modes. Okay, so two. So that explains the two over here. Now, where does this SL cube ST cube comes from? It's really writing your dispersion relation. Your S is your speed, is given by omega over k. This is actually just like your phase velocity equals to frequency times the wavelength. Okay, so this is just in terms of angular version. So S equals to omega over k. So that, for example, will tell you k equals to omega over s. And you remember in your the k here, you have k squared, some constant here. Okay, let me just that constant times k squared dk. So you're going to get k squared, which is omega squared over s squared, times dk. You have another s at the bottom that gives you the s cubed needed on top. Now, this is assuming that you have these two different modes traveling with different speed. Now, one could sort of define an average kind of speed as bar by the following. So there are three different modes. This is taking the three different modes, and then you have S bar cube. This should be given as 1 over SL cube plus 2 over ST. So this is just like defining your average. So with this, you can simplify a little bit what you're going to do. So you have this set, going to do d omega, the density of states is now equals to 3v over 2 pi squared s bar cube omega squared d omega. Okay, let's write down the free energy. Remember the free energy of the oscillators? F equals to n epsilon plus 3 kBT V on 2 pi square s bar cube. And then the integral over omega from 0 to infinity, omega squared log of 1 minus e minus h bar omega on kBt d omega. Now, in order to do this, it's just like the same thing that we've done for the case of black body radiation. So we need to integrate this by parts. So let me just write down. So so you consider, for example, this as let me just check. So this is going to be like your omegas, okay, integrate by parts, omega squared d omega is dv, and then the rest is u. Okay, so you do that. I'm going to just to write down what's there. F equals to n epsilon minus 3 kbt v divided by 2 pi square s bar cube, and then the factor coming from the integral h bar kbt, and then the thing coming from integrating this v du, so 1/3 omega cube there, and then your differential of that e minus h bar omega on kbt divided by 1 minus e minus h bar omega on kbt d omega. Now this looks, we can simplify this by changing variables, just like again in the previous case of the black body radiation. So I'm not going to repeat that. Oops. I'm doing n epsilon minus 3 kbt v on 2 pi squared s bar cube, then h bar on kbt from the previous one, and then changing variables, might be in the case of black body radiation, or so that you can simplify what the integral is. This is to the fourth, and the integral from 0 to infinity of z cubed divided by ez minus 1. So without going too much into the detail, we can look up this in table of integrals. This is essentially pi to the fourth of 15. So let me write down the final answer. So this is equals to n epsilon minus pi squared kb fourth t to the fourth after simplification over 30 h bar squared s bar cube. So from there, we can now calculate your entropy, for example. So I'm just going to write down the answer: 2 pi squared kb fourth t cube e divided by 15 h bar squared s bar cube, and finally the heat capacity. Which I just simply write down the answer: 2 pi squared kb fourth t cube v on phi h bar squared s bar cube. So one can look again at the limits of this extreme limits of this heat capacity. So here for low temperatures, where Einstein's model had problems, for low temperatures, one finds that Cv is proportional to T cube. And then for high temperatures, again, I'm not going to go through all of this. For high temperatures, you get back to the same limit as the Einstein model, which is the Dulong-Petit's law. Cv, the full working is actually inside the book, so I'm not going to do it. Okay, so that's that. There is another deviation at the low temperatures. Still, it says deviations over here, which corresponds to the conduction electrons, which has its own contribution to the heat capacity. Okay? So this will have to be treated when you treat electrons as fermions, which is, I hope to put this in another lecture. So let's do one final thing that Debye introduced. Debye introduced a cut-off frequency. Called omega d, or label omega d, which is known as Debye frequency. Now the idea is essentially to make the integration simpler. So let me write the density of states first. Below this Debye frequency, we have the same density of state like before, which is 2 pi squared s bar cube, and then omega squared d omega. So this is for omega less than omega d. But for omega greater than omega d, we assume it to be 0. So this is a simplified picture saying that higher frequencies sort of contribute negligibly. In fact, you already seen that as you go higher in frequency, higher in temperature, for example, then you expect this Dulong-Petit's law to appear, contribute negligibly. So what's the point of this? Then you can now do the integration. Okay, so the integration is now okay. The total number of modes is still the same. (3n). Okay, but now you have this to be equal to this integration 2 pi squared s bar cube. You remember we need to integrate over all modes, but now you're only doing it to a finite case. And that can be integrated easily to give you this. And from that, you can invert that or rearrange it to get your Debye frequency. 6 pi squared n over v. And So this is like a cut-off frequency. So h bar omega d, which is essentially dimension of energy, is called the Debye energy. And Debye energy can be related to what is called the Debye temperature. The D, which is given by h bar omega on divided by your Boltzmann constant. This is Debye temperature. In fact, one can actually calculate this for several materials. I think in the book it does mention that. So let me just go that. So is the Debye frequency temperature here. Oops, that's not what I want. Is that here? So here is some of the Debye temperature. So in some ways, this can be tested sort of experimentally nowadays. Okay. So I'll stop there for now, and I'll continue with the other chapters in the book until I feel that's enough for the final exam. Thank you, everyone.